Hi. Good morning. I'm at home, but it may be noisy due to because the water facility in my in the bathroom in my house is being fixed. That's why drilling. Now it's quiet, but I'm sorry if you feel noisy. Okay. はい。Today is the last time, last lecture in 2020, okay? In January, we will resume, okay? I have received many reports from you. After this class, I will enjoy reading them. Okay? はい。Today, I will start the second latter part of my lecture related to seismic design, okay? はい。じゃあ、gradually I will start. で、はい。First of all, last weekend, かな 2 weeks ago, I made an invited lecture for Innes University of Jemba. Actually, Dr. Dr. Retno, female researcher who graduated YNU, coastal engineering laboratory. She organized, maybe she invited me. Then I made a lecture about earthquake disaster mitigation. Okay, so hi. Today I will give you same kind of contents, okay, as an introduction for seismic design. Hi. So maybe around 10 years ago, Dr. Retno was my student, like you, in this kind of lecture. So recently you can easily invite us on online lecture, but I'm not sure I will accept your offer in the future. If I am free, I'll accept your offer. はい。で、ですね、ちょっと待ってください。Before starting the contents, はい。I hope some of you have briefly read the journal paper written by Dr. Ishibashi. Actually, he is Dr. Ishibashi. Okay. Today we will start studying his paper. Okay. Now he has retired railway company, but still he is working as a kind of advisor, special advisor for consulting company, okay? Railway consulting company. He was or he is the top railway engineer, okay? The Professor Maekawa respects him also, okay? He was belonging to East Japan Railway Company, JR East, okay? The biggest railway company in Japan. Now it's a private company, but before he belonged to National Railway, Japan National Railway, okay? He is also one of my teachers, okay? I learned lots of things, lots of philosophy or lots of knowledge or way of thinking from him or from his stuffs, okay? That's part of me, okay? also I learned from Professor Okamura and Maekawa Sensei, etc. So you are learning those philosophies through me. Okay, he is Dr. Ishibashi. はい。で、I will, okay. So you already have this paper, right? Invited paper. Again, it's included in Journal of Advanced Concrete Technology, okay? Organized by JCI, Japan Concrete Institute. He is Dr. Ishibashi. Dr. Ishibashi. From this paper, you can learn the philosophy of seismic design and also seismic retrofitting or rehabilitation techniques, okay? Developed by them. So I hope you can learn many things. Okay? はい。で、ちょっと before starting, okay, I will show you one picture. In that invited lecture for Indonesian University, actually more than 200 audiences. Okay, so I was so much surprised. I gave that invited lecture from Fukushima Prefecture because I was on a business trip, okay, for technology development for tunnel construction. So I took this picture from my hotel in Fukushima Prefecture. Do you know Fukushima Prefecture? Nuclear power plant accident happened in that prefecture. Okay, so it's away from Tokyo or Yokohama. That's why you can find a kind of rural residential area. But I hope you can see Shinkansen structure. Okay, it's called railway viaduct. 鉄道高架橋。で、can you see Shinkansen? Okay. This is one train. Green one and white ones are connected. Okay. So very long trains. Okay. So this kind of railway viaduct, elevated bridge, is common in Japan. Okay. So can you see columns? Or can you see middle beams? Okay. And can you find some retrofitted columns by yourself? Just a moment. どうやってでかくする？あ、これか。For example, this column, these columns in white color are retrofitted. Okay, you will learn later. Okay, so this one, this railway viaduct located in Fukushima Prefecture is also retrofitted. Okay, without this retrofitting, the columns can fail. Okay, the whole railway viaduct can collapse. Okay, okay. Can you imagine? Actually, you can find these retrofitted columns almost everywhere in Japan. Okay, so please observe. After this lecture, you can understand the basic matters about seismic retrofitting. So you can easily find those retrofitted columns, okay, in Yokohama or Tokyo area. Okay. はい。Okay. Then slowly I will go into that paper. Can you see this one? Okay. はい。Before going into detail, so figure 2, in the picture I took, you observed the healthy standing railway viaduct, right, in Fukushima Prefecture. It can fail like this. Okay, this is the real actual damage happened in Kobe earthquake in 1995. Okay, so without those retrofitting, please wait. はい、どうぞ。すいません。Work hard fixing water facility. はい。Okay, so this is again severely damaged railway viaduct. Okay, I will show you another typical Shinkansen structures. Okay, this is not rigid frame structure, but long girder. Long girders are supported by piers, etc. Okay, so different type, but anyway, in Japan, due to several reasons, these elevated bridge, kokakyo, elevated bridge, are common. Do you know why? Why we need to construct those elevated bridges? Do you know why? It's very rare to see those elevated bridges in European countries. It is. Okay? One of the, I think several reasons, but one of the reasons is that in crowded areas, okay, elevated bridges do not disturb the transportation, right? Okay. If the Shinkansen is running on the ground, it will disturb the crossing transportation. So maybe that's one of the reasons. Okay. And second reason, which I heard, that sorry, now it's noisy, right? Sorry. すいません。My voice is clear? It's okay?
It's okay, it says.
Sorry. Second reason is that the ground condition is not good. Okay? So Japanese ground condition and for example European, for example France, ground condition is so much different. Okay, so it's almost impossible to put the track directly on the ground. That's why we need to build piles or columns, etc. Okay, structures are necessary. Okay, I think those two are the main reasons. Okay? さっき見せたような高架橋とか、ごめんなさい、RC、ラーメン高架橋、ごめん。英語で rigid frame って言うんだけど、rigid frame。日本ではよくラーメン高架橋って言いますけど、最初に見せた写真ね。とか、あと、後半に見せたのは、橋脚があって、一本の橋脚があって、上、桁が支えられて、ああいうのが鉄道では典型的なんですけど、さっき英語で説明したことだけど、地べた走ってると邪魔になるよね。左右分断するんで、それを避けるっていうのも一つあるし、地盤が悪いので、ヨーロッパみたいにドンと地べたに軌道とか作ることができないよね。それが多分理由だと思います。Okay, so that's why we need to construct so many numbers of bridges. Okay, very long elevated bridge line. That's why it should be cheap. So that's why that kind of rigid frame, a kind of standardized structures were developed and constructed. Okay? はい。で、いきます。It's noisy, but it can be helped. はい。じゃあ、じゃあ、we will study together, okay? Starting from そうですね。abstract. Okay, let's read abstract together. Okay. はい。じゃあ、どうしよう。Wichuda さん do you read?
はい、先生。
The abstract.
The abstract.
Yes.
The Miyagi Prefecture earthquake in 1978 was the first earthquake to cause serious damage to railway concrete structures in Japan.
Hi. Do you know where Miyagi is? So you don't need to remember, but you are living in Japan, right? So please learn lots of things about Japan. Do you know where Miyagi is? No?
I heard about it, sensei, but I don't know.
Okay, I see. Do you know Sendai? Sendai.
Sendai.
No, okay. So after Corona, COVID is settled, okay, please visit many towns or cities, okay? Japan has so many fascinating cities or areas, okay? Please do not stay only in Yokohama, please, okay? So Sendai is here, okay? It's a kind of capital of Tohoku area, okay? So Miyagi Prefecture covers this area. Okay? So, はい。Figure 1 is related to that information. Miyagi Prefecture earthquake. はい。Go back. はい。So in 1978, at that time, Dr. Ishibashi was engaged in the construction of Tohoku Shinkansen in this region. It was under construction. That's why he experienced this serious damage, severe damage, okay, at the site. So he gradually accumulated knowledge about damage, how to repair, how to restore, okay, how to improve seismic performance for new structures, etc. So he is a real engineer. Hi, Wichuda-san, go ahead. This was?
Hi. This was followed by South Hyoko Prefecture earthquake. Hyogo, sensei, sorry. South Hyoko Prefecture earthquake in 1998, with the failure of column of RC viaducts carrying the Shinkansen bullet train and old railroad lines, predating in 1983 seismic design standard as the result.
Okay. So this is a very famous Kobe earthquake, okay, in 1995. One of the very important keywords in the this seismic design lecture is shear failure, okay? Shear failure is a very important keyword, right? Then, hi, please go ahead.
As the result of various concrete structures sustaining extensive damage never experienced before, the seismic design standard was greatly revised, and the seismic rehabilitation of existing structures was started on a full scale.
Okay, so there are many keywords, but seismic design standards was revised. Okay, so we need to revise design code. Okay, if we find some problems. Okay, so that's the basic attitude or basic stance. Okay? はい。Some engineers, or I heard that many engineers, or almost all the engineers, are just following the standard or manual. Okay, one very famous engineer called them as manual engineer. Okay, but we need to revise. Right? So you will learn how we revise the Japanese design course based on the lessons from severe damage. Right. Okay. Uchida-san, thank you. So, next. Who? じゃあ、エドムさん。Basic concept?
Basic concept of seismic rehabilitation.
Sorry, I cannot hear you, sorry.
Can you hear me? Hello?
Hello?
Can you hear me now?
Not so well, sorry.
Oh.
Okay, I can hear you, sorry.
Okay. Basic concept of seismic rehabilitation is to prevent shear failure of columns that lead to the collapse of reinforced concrete viaducts and breach. Catastrophically occurred in the whole structural frame during the past large earthquakes.
Yes. So again, we need to prevent shear failure. Okay. Otherwise, as you saw in the picture, RC viaducts can collapse, totally collapse. Okay. Hi. Please continue.
To enhance the seismic capacity of the whole structural frame, increase the ductility of each column through seismic rehabilitation capable of absorbing seismic energy is needed.
Yes. So again, next keyword, ductility. Okay, it's different from strength. Okay, so we need to increase the ductility. Okay? That's very important keyword. Right? And by increasing the ductility, energy absorption performance is also increased. Okay. はい。はい。じゃあ、next.
Shall I continue?
Yeah. if you want. Okay, please continue.
As the space under many railway viaducts is used by stations and shops, negotiation regarding the relocation of businesses, the removal of large obstacles such as heavy machinery, and the development of valid seismic rehabilitation methods to reinforce a large number of massive columns were called for.
So, for example, this kind of situation. It's not so clear, sorry. This is better, okay? So, I think you can find this kind of situation so often in Japan. So the space under the viaduct, RC viaduct, is used for shops or etc. In this case, maybe restaurant. Cafe and restaurant, Mona Lisa, open. So we cannot disturb the operation of these shops. Okay? That's why special techniques are needed. Right. But it's a kind of typical Japanese way of thinking. Okay, so but for solving these practical problems, many techniques are developed. So I think very typical Japanese situation. Okay? はい。ちょっと待って。はい。The final sentence.
At present, we are trying to enhance seismic capacity as much as possible for new structures in order to prevent serious damage and enable early restorations.
Yes. So, improved seismic design for new structures and seismic rehabilitation, retrofitting are both treated, explained, or discussed in this paper. Okay. So please try to learn as much as possible from this interesting and practical paper. Okay, can I go ahead? Or any questions so far? 大丈夫? Okay. Yes. Then, So, here, 1978 was the first lesson for my first big lesson for my civil engineers, okay, or railway engineers. In Japan, maybe you should know, or you should bear it in mind that the building engineer and building design code and road or railway engineering code are different. Okay? So, in this lecture, I will tell you the history of railway engineering. So it's a bit different from building design history. Okay? But I think the basic concept is not that different. Okay. Anyway, in railway engineering, 1978 was the very big lesson, okay, from earthquake. That's why a design standard was revised in 1983. Okay, this was the first big revision in railway engineering. After that, in 1998, again, very big, two big lesson from Kobe earthquake, and we made further revision. Okay. はい。で、do you know when Kobe earthquake happened?
Yes, Sensei, I think. Sensei?
Yes.
Kobe earthquake was happened in, according to my memory, in 1995 January. I don't remember the exact day, but it's in the morning, in 6 or yes, in the very early morning. Yes.
Okay. So January 17th. Okay, 17. The time is also very important. 5:47 a.m. 46 or 47. Maybe 47. So please check it later. Okay. It's very important because the Shinkansen operation, Shinkansen running, Shinkansen operation is started at 6 a.m. Okay. So please never fail to use Shinkansen, okay, while you stay in Japan. It's very convenient. It's so fascinating system, okay? But please, okay. Actually, I like Shinkansen so much. で、So what would have happened if that earthquake happened after 6 a.m.? Okay. So, Shinkansen system in Japan is very busy, okay? Very busy schedule. It's so much different from European countries, etc. Especially Tokaido Shinkansen, which is connecting Tokyo and Osaka. It's so busy, okay? So, can you imagine? Before 6 a.m., Shinkansen trains are waiting for the operation at each station. Okay, at each station. At 6 a.m., all the Shinkansen starts. Okay, depart from each station. Okay, so I cannot imagine, but I don't want to imagine what would have happened. But if that Kobe earthquake happened after 6 a.m., the RC Viaducts collapsed, right? In the worst case, running Shinkansen went down to the ground from the viaduct. They may be crashing houses, and so many numbers of people must have been killed. Okay, so Shinkansen is a kind of symbol of Japanese technology. Okay, that symbolic technology killed so many numbers of people. Okay, maybe if it had happened, maybe. So I know. I don't want to imagine, but okay. So I myself or some engineers think that God gave us a chance, okay, to learn. Okay. So after that, we revised the design code, and of course, so many numbers of uncountable numbers of structures have been retrofitted, okay, to be resilient. Okay, of course, the recent new structures have very high seismic performance, etc. Okay, so it was a too large lesson, but we Japan learned a lot. Okay. はい。で、and I told you that Shinkansen operation starts at 6 a.m., right? Every day, okay, every day in Japan, between midnight, I mean 0 a.m. and 6 a.m., the maintenance is conducted for all the track every day. That's one of the reasons for the safety of Shinkansen, Japanese Shinkansen structures. はい。で、I'll go back. Okay, so chapter 2, seismic damage of railway RC structure. So here, due to Kobe earthquake in 1995, fortunately, as the earthquake occurred in the early morning, accidents involving trains falling from RC viaducts and bridges did not occur, okay, as I explained to you. はい。で、here, ちょっと someone please read this paragraph. Okay. Who can read it? この人。A. Honey So-san. Are you there?
Yes, I'm saying.
Please.
Which paragraph?
This one, the first paragraph of chapter 2, the Miyagi Prefecture.
Oh, yes. The Miyagi Prefecture earthquake in 1978 caused show damage at many railway facilities, such as RC bridges and RC piers. In response, the
sorry.
restrainer cables...
Okay. Please. Sorry. Okay. Shoe damage at many railway facilities. Hi.
Yes.
This one. Okay. Support. Okay. I don't know the situation in other countries, but in Japan, especially in old structures, these metal devices, this is a part of shoe, right? Part of support. They are broken in Miyagi Prefecture earthquake in 1978. Do you know the reason? It's a cast iron. Cast iron. Okay, it's very convenient to make any shape devices. Okay, cast iron. It's different from steel. Okay, so cast iron is very convenient, but it's brittle. So that's why cast iron bearing devices, shoe devices, were broken. Okay, so recently we never use cast iron. Okay? Is it clear? これ芋のシューって支障、こういう鋼じゃなくて芋のです。鋳鉄、ごめんなさい。鋳鉄は型に流して作るのですごく便利なんですけど、脆性的、脆い、鋼みたいに伸びない。だから地震でたくさん壊れました。今、鋳鉄は使われてません。こういう支障にはね。はい。So maybe many of you know that recently steel support, steel shoe or rubber shoe, rubber support are widely used instead of cast iron. はい。sorry to disturb. はい、go back. はい。In response?
Yes, in response, strainer cables have been installed and bridge movement joints and brackets have been attached to the abutments on all railway lines in Japan. However, before the South Hyogo Prefecture earthquake in 1995, no seismic rehabilitation for RC stretchers have been conducted except for measure stretchers except for measure provided against the Tokai earthquake in the 1980s and activated for the Shinkansen in the Shizuoka area was reinforced with steel plate jacketing and connecting adjacent provided with pre-stressing cable.
Okay, thank you. Hi. So many local names of cities, so it's a bit difficult for you, but if you're interested, please try to learn. Okay. Hi. So before 1995, okay, before 1995, almost no seismic rehabilitation had been done, okay, except some area. Okay. So do you know Shizuoka? Shizuoka is in this picture, so in this map, located here. Shizuoka Prefecture, there is a very famous mountain, Mount Fuji. Mount Fuji is located in Shizuoka Prefecture. So, okay. So only, only near the Shizuoka area is seismic retrofitting was conducted. Why? I showed the Google map. ストに行けるのかな。ちょっと待って、please wait for a while. いけるか。Sorry. Can you see this one? Can you see this map? Okay. はい。Now, some of you or many of you are near here, 東京、横浜 area. Okay. 静岡 is near here. 静岡 is here. Mount Fuji is also near here. So can see a trench, big trench. Okay. So this trench caused a Great East Japan earthquake. Okay. Here also you can find a trench, okay, big trench. So it was believed that this trench will cause Tokai earthquake soon. Okay. The last earthquake happened, I think, more than 150 years ago. 150 years ago, long absence. Okay. That's why it was believed that this area, Shizuoka area, will be attacked by Tokai earthquake soon. That's why seismic retrofitting was intensively conducted for Shinkansen structures only in this region. That's the reason. Right, so scarce for map. Indonesia is also facing same kind of risk. 頑張りましょう。Okay. I'll go back. Okay, again, this area, Shizuoka area. On Tokaido Shinkansen, the first Shinkansen connecting Tokyo and Osaka through Nagoya and Kyoto. Okay, this is the first Shinkansen. はい。So again, now you have a better knowledge. Sorry, here. However, before Kobe earthquake in 1995, no seismic rehabilitation had been conducted except some measures, countermeasures against Tokai earthquake. Okay. In the 1980s, RC structures for the Shinkansen in Shizuoka area was retrofitted, reinforced with steel plate jacketing. Okay, it is. Hi. Okay, so I'll go back to the map. So without the tremendous efforts by civil engineers, okay, only this region, the structures near Shizuoka area have been retrofitted. It means that all other structures were dangerous. Can you imagine? So this is showing just the this thick line. Thick lines are showing Shinkansen network. Okay. So of course, many other but conventional lines, local lines, okay, all of them were in dangerous situations, okay, with the risk against earthquake. Okay. Very dangerous situation. So bad design code or design code without sufficient knowledge will cause this kind of not resilient situation. So after the earthquake in 1995, Kobe earthquake, what happened? Okay, Japanese government instructed to retrofit railway structures only in mega cities like Tokyo, Sendai, or Osaka, or Fukuoka, etc. Okay, so civil engineers started to retrofit the structures in big cities. It takes time, okay? But it means that all other structures in local areas remained weak. Okay? So that history is explained here. Yes, here. Following Kobe earthquake, the Ministry of Land, MLIT, Ministry of Construction, instructed railway operators to conduct seismic rehabilitation to prevent shear failure of columns. Okay? At first, the target area of seismic rehabilitation was limited to overcrowded lines in Sendai. Kanto means Tokyo area, Tokai, Kinki is Osaka area, etc. Okay. はい。で、it takes time. Okay. After that, 2003, 8 years after Kobe earthquake, again, one earthquake happened. Okay. In local area, rural area. Actually, at that time, 2003, I was working for a railway company. Okay. So I experienced this earthquake, okay, as a railway engineer. This earthquake, where is this earthquake? Okay. This one. Number 3, Sanriku Minami earthquake. Okay. So number 3 earthquake happened in 2003. Okay. It's away from Tokyo, it's away from Sendai, but severe damage happened in local area. Okay. We should understand that the railway, especially railway, okay, different from roads, railway is a line. Okay. Line infrastructure. Okay. So when some portion, some points are damaged, the line doesn't work. Okay. So, but railway company, JR East company, recognized that not only city areas, but all the structures should be retrofitted, have to be retrofitted. Otherwise, railway infrastructure as a line, okay, doesn't work appropriately. Okay? Okay? That's the decision. That's a very big decision for moving toward a resilient country. Okay? はい。この大都市の補強を優先してやってきたんですけど、この丸3の地震、三陸南地震っていうのが、私が JR で働いている時に発生したんですけど、それなりの被害が出ました。いわゆる田舎で。で、結局大都市だけ補強しても、田舎で損傷が起こると、結局ラインが機能しないんだよね。だから、この2003年の地震を契機に、少なくとも JR 東は全部補強すると決めました。はい、だから、そういうステップバイステップで来てるんですけど、そういう努力がなければ、日本全国の鉄道のインフラが ああいう壊れ方をしてもおかしくなかった。恐ろしい状況です。OK? はい。はい。That's the rough history of seismic retrofitting. Okay? It's step-by-step retrofitting, but still now we are continuing. Okay? So I will finish this explanation by adding one more information. Okay? So as you know, or as you remember, okay, big earthquake in 2011, March 11, nearly 10 years ago, almost all the coastal line in eastern Japan were damaged, okay, both by earthquake and tsunami. I almost believe that without those retrofitting, very many structures must have collapsed. It's a kind of nightmare. Okay. So we could be in time. We could avoid very severe collapse of RC viaduct. Okay? That's a kind of result by obtained by civil engineers' efforts. Okay? Again, we learn so much from Kobe earthquake. はい。After this one, I'll go into technical points. But do you have any questions so far?
Sensei.
はい。
How about for other structures such as buildings or bridges? Were there any changes after
Of course.
Yeah. Were there any collapses too?
In that earthquake?
Yeah, Sensei.
Of course, yes. So, if we talk about buildings, very big design revision was made in 1981. Okay, 1981. So the buildings design based on all design codes before 1981 are weak. So if you are living in very old apartment, please take care. Okay? It can be crashed. で、road structure was similar, but I will explain the railway design history because I know it the best compared to building design TC. And another reason is that the design philosophy is very clear. Okay? That's why for example, ductility or ETC, or how, sorry, I'll explain later, but it's clear. That's why I'm selecting railway engineering topic. So in Kobe earthquake, many houses were crashed. So if you want, I can show you a kind of computer graphic, CG anime, sorry, CG movie. はい。Any other question? はい。じゃあ、let's go ahead. ですね。 っと待ってね。これないか。はい。じゃあ、please read this part. Basic concept for seismic rehabilitation. はい。じゃあ、ファンさん。
はい。
3.1 Basic Concept。うん。
はい。
ちょっと待って、ここだけ。
あ、
Please.
はい。The basic concept of seismic rehabilitation is to prevent the value of column members caused by large earthquakes, resulting in the collapse of RC viaducts and bridges, which are catastrophes that have occurred in past earthquakes. To enhance the seismic capacity of the whole structure frame, the aim is to increase the ductility capacity of column members through seismic rehabilitation in order to allow better absorption of earthquake energy, but enhancing the electrical structure of the column members is not properly done.
ちょっと待って。
The reason for this is that if the fracture strength of the column members damaged by an earthquake is enhanced, future earthquake damage may occur in beam members and the foundation members. Since repair and strengthening of beams and foundation members is more difficult than for column members, it is considered important to restrict damage after seismic rehabilitation to column members.
Thank you. はい。The philosophy is summarized in this paragraph. Okay, so it's very important. So please try to fully understand the essences or related technical matters. I will explain today, and also I will continue next year. Okay. はい。Again, first of all, shear failure should be prevented. That's very important aspect, okay? But you should know how you can prevent shear failure, okay? And next one, great, here, increase ductility, okay? Okay, so let's start from this one, okay? What's ductility? So we should jump to the final figure, okay? This one. You can see figure 27, okay? I'll explain. Let's magnify the figure. はい。Yes. So, what's this figure? Vertical axis is strength ratio, P over P yield. Okay. What's horizontal axis? Plasticity rate, delta over delta yield. Okay. So, have you seen the column test? Where is it? Today I cannot use whiteboard, so どうしようかな。ちょっと待ってね。これ it's a bit difficult to explain. Okay, so I have not shared this PowerPoint file yet, but sooner or later I will share. Okay, can you see this PowerPoint file? Okay, okay. So this is column. Okay, this one. This is reinforced concrete column. It's painted in white so that the cracks can be easily observed. Okay. This column is fixed on the base. Can you imagine? This base is fixed on the footing is fixed on the ground. Okay. After that, we will apply horizontal load here. The column will deform into this direction. Can you imagine? This is the horizontal load, and this is the displacement. So here cracking happen, and yielding of main reinforcing bar, the maximum load, and finally load is decreased. Okay. So this is a typical load displacement relationship for reinforced concrete column. Is it clear? Okay. So please have a kind of image about load displacement relationship for reinforced concrete column. Okay. I'll go back. Okay. This is again load displacement relationship, but it's normalized by yielding load, and it's normalized by yielding displacement. Okay. So here it's around 1.0. That's why the load became larger, higher than the yielding load. Okay. Here around 10. So 10 times larger than the yielding displacement. Okay. Okay. The red one is showing a larger displacement, so higher ductility. Okay. So this is again load displacement relationship. So this area is showing the seismic energy absorption performance. Okay. So reinforcing bar is already yielded, but by this large deformation, seismic energy, earthquake energy can be absorbed. Okay. This is ductility. Okay. Shear failure can happen like this. Okay. Without showing ductile behavior, shear failure suddenly happens. Okay. Sometimes before reaching yielding load. So in this graph, before reaching 1.0 at around 0.7 etc, suddenly fail in shear. So almost no energy absorption. Okay. So it's very brittle and it's very dangerous. Okay. Hi. Now, do you have some image about ductility? Okay. Hi, I'll go back. あれどこだ ?3.1 here. Okay. Hi.
Hi. You said in the column test.
Yes.
Hi. Is it the just axial load plus combined with the?
Yes. Sure. We should apply the equivalent actual load. Okay.
Okay. And how about horizontal? Both combined together.
Of course, yeah. Actual load is kept constant. The horizontal displacement gradually increased. Sorry, column like that. Okay. The reverse cyclic loading. something like that.
はいはい、わかりました。ありがとうございます。
はい。大丈夫? Can I go ahead or any question? Any more question? はい。OK。And yes, so I have explained about ductility, okay? Of course, you can learn more or you can learn more deeply in January. Today, please try to catch my essential keywords or essential points or a fundamental idea about important aspects, okay? はい。The next, shear failure should be avoided, right? I'll talk about this point. How can you prevent shear failure? I think this example is the easiest way to understand the idea. Figure 8 is showing one of the methods, okay? Actually, very many numbers of methods have been developed, okay? This is called Rebar Method. Do you know Rebar? You will also have rib, okay? Near the stomach, okay? It looks like rib, right? リブ、あばら骨。あばら骨みたいに見えるでしょ？うん。So this figure 8 is the conceptual diagram of Rebar method. It's called RB method. You can find this method in Yokohama or Tokyo area, okay? If you observe carefully. Hi, this is clear, okay? So shear reinforcing bar is added outside the column. Is it clear? Shear reinforcing bar was insufficient in the original column. That's why they are added outside the column. Very simple method, okay? Okay, so again, how can you prevent shear failure? You should increase the resistance against shear failure. It's clear, okay? But there are many kinds of methods, okay? Hi. Today I will not go into very detail, but please have some image, okay? で、はい。Compared to that RB method, Rebar method, this is more common. Steel plate jacketing, okay? It's also used to increase shear capacity, okay? It's different from reinforcing bar, but these steel plate are covering the reinforcing, original RC column, okay? But it's similar to Rebar method, right? Okay? It's discrete, separated steel, but if you connect all, okay, it will be like steel plate, right? But you can find construction machinery, okay? So of course, steel plate is very heavy. That's why in this kind of open space, utilizing construction machinery, you can use steel plate jacketing method, okay? But here, there's a wall. Okay, so it's very difficult to break, demolish all these concrete wall. That's why only small holes are made. Okay, the manually reinforcing bars are installed, then tighten at the corners. Okay? That's why for solving this kind of difficult situation, RB method was developed. Okay. はい。ちょっとthis is the explanation about how to prevent shear failure. So, do you have any question?
先生、
はい。
リブメソッド
リブバー、
リブ、はい。っていうのは、how do we suppress corrosion?
OK。coated, it's coated by なんだ、not titan, but not epoxy coated, but it's coated to prevent corrosion.
先生。
塗装されてます。
はい。
裸の鉄筋じゃない。It's not a bare bar. いいそれで。
はい。裸に見えました。
裸ではない。亜鉛メッキとかそういうやつ。
ありがとうございます。
はい。Sorry, another question? Any other question?
Sensei, our carbon fibers were also utilized
yes.
as shear reinforcements.
Yes, it's just like steel jacketing method, okay? Here. So carbon fibers, this is also, yes, FRP sheet. It's okay?
Yes, Sensei.
Carbon fiber is one of the FRP sheets. So it's light, and one of the merit is lightness, okay? Hi. Any other question? Hi, okay. So anyway, by utilizing those methods, shear strength is increased, okay? Shear strength is increased to prevent shear failure. Hi. We will go back to that important paragraph. Hi. Next important aspect is this one. As I told you already, shear failure should be prevented, but enhancing flexural strength should not be done. Okay. Again, flexural strength should not be increased. Flexural strength should not be enhanced. Okay. Do you understand? Again, let's go back to steel jacketing. Okay, hi. So please observe precisely the length of the steel plate. Okay, from here to here, right? So if the steel plate is longer than this one, for example, the bottom of the steel plate is much lower than here, for example, in the underground part, what will happen? I mean, with longer anchorage, okay? This steel plate will act as reinforcing bar, right? Longitudinal male reinforcing bar. Is it clear? If so, flexure strength is also increased. Okay, so if you have some fundamental knowledge about reinforced concrete, it's clear, I think. Okay, so Dr. Ishibashi, the author, is saying that that should not be done. はい、ちょっと日本語で言うと、これ後半巻き補強ですけど、後半の巻き立て補強ですけど、ここが一番てっぺんで、ここが一番下。で、柱の、これ下にフーチングがあるんですけど、この後半の下がもっと深いところまで入ると、定着取れますから、この後半が曲げ補強に効いちゃうわけ。主敵みたいに作用しちゃうわけ。ここで切ってるから、これ定着ないので、曲げ体力ほとんど上がりません。Okay? それをするなっつってるの。Okay? Again, due to this length of steel plate, flexure strength is not increased a lot. I think almost zero. Okay? Increment of flexure strength is almost zero. Okay? Only shear strength is improved. Okay? All right, let's go back. This is very important point. Okay? The reason for this, yes. The reason for this is that if the flexural strength of the column members damaged by an earthquake is enhanced, future earthquake damage may occur in beam members and foundation members. Okay? はい。So this sentence is saying that the damage should be concentrated in column members. Column members should be damaged. Okay? The author is saying like that. Otherwise, foundation will be damaged or beam will be damaged. Okay? It's very easy to understand that how difficult it is to repair or restore or inspect the damages of foundation. Okay? You need to excavate. Okay? It's almost impossible. Hi. And also if beam members are damaged, it's very difficult because the tracks are also severely damaged. Okay? はい。So, ちょっと待って。Okay, so, どれがいいかな。So that's why, as you can see in this picture, or 全体像の方がいいな。ちょっと待って、ごめんなさい。あれこれでいいか。はい。As you can see in the first picture, this is Fukushima Prefecture, RC pad. So here, only columns are retrofitted, okay, to increase shear strength. Again, flexural strength of these columns should not be enhanced. Otherwise, beams will be failed, or you cannot see the foundation, but foundation can be damaged. Okay? We should avoid such kind of difficult damage to be restored. So I like this philosophy, okay? So maybe we can call this strategy or philosophy as structural balance. Structural balance should be kept. structural balance should be well considered. Okay, structural balance should be managed, etc. Okay, it's very clear concept and practical concept. Considering total performance, okay? Even after the earthquake, they need to repair, they need to restore, okay? They need to reuse the structure, okay? ここ多分すごく大事で、これ柱だけ補強してるのよく見えると思いますけど、柱の先端破壊は絶対防がなきゃいけない。で、ここ曲げに強くしちゃうと今度弱点が他に移るので、この針が壊れたり、見えてないけど基礎が壊れたり。でどちらもすごく直すのが大変だし、針なんていうのは軌道にも影響を直結するので、そういうのをさせないと。だからさっきストラクチャーバランスって言ったけど、構造バランスをちゃんと考えて、後の復旧性とかも考えて、頭を使って補強していると。ここは多分すごく大事だと思うね。はい。So this is a very important point. So, do you have any questions so far? Ductility and shear failure should be prevented. And furthermore, structural balance should be managed or well organized. Okay. Maybe this is enough for today's introduction, but do you have any question?
Sensei.
Yes.
I have a question
yes.
about in paper. I see that in figure 2 and
figure 2. Sorry. Wait. Figure 2.
Yes.
Which one? Figure. This one?
Figure 2.
Yes.
Figure 2 and figure 4.
Mm-hmm.
I see that the collapse in figure 4 is happened in the middle of the column, but in figure 2 is in the top of the column, which is connected to the beam. So, is there some reason for that?
I see. Sorry, this is a bit difficult. It's a bit difficult to identify what happened in this figure 2, okay? It's not the top. I want to use whiteboard, but ちょっと待って。Maybe I should use different picture. Can you see this PowerPoint file?
Yes.
Which will be shared later. Okay. Okay. Yes. Can you see this one? So maybe this slide is better for you to understand. Okay. RC columns are severely damaged by shear failure. Okay. Shear like that. Okay.
Yes.
As you pointed out, it's nearer to the top of the column. Okay. There must be a reason. There is a reason. Okay. It's near to hinge point. Okay. It's but it's known that the shear capacity is decreased in hinge portion due to the effects of bending, crack, etc. Okay. So maybe I will explain it in the next class, January. Okay.
Oh, okay.
And anyway, shear in this real structure, shear failure happened here. But I should show another bit. ちょっと待ってください。 wait for a while. これか。But it depends on the situation. Okay. Can you this another slide?
Yes, Sensei.
For example, in this case, the shear failure didn't happen near the top of the column. Okay. In this case, just in the middle. Okay. It depends on the original design. In this case, the shear strength near the middle of the column was very low. That's why shear failure happened here. So it depends on the strength. Okay.
Oh.
Okay.
Okay. Okay. So it
that's one of the answers to you. Okay.
Oh. Okay.
I need to sorry, add one more information. Sorry, figure 4. Okay, this one. You asked about this damage also, right? All right, can you see?
Yes, yes.
Okay, so there's a clear reason why damage is concentrated in the middle. There's a clear reason, okay? So this is also explained in January, but some of the main reinforcing bars are cut here. Okay? Cut. Because for this column, moment distribution will be like that. Near the top, moment is very 0 because there is a support here. This is a simple column. Okay?
Okay.
So bending moment becomes the maximum at the bottom, right?
Yes.
That's why near the upper portion, reinforcing bars are not necessary. So that's why some of the reinforcing bars, longitudinal reinforcing bars, are cut here. That's why. Do you understand?
Oh yes, I know.
So that caused this damage. I'll explain more in detail in January.
Okay, I know. So it's related to the reinforcing bars.
Yes.
Okay. Thank you, Sensei.
So your question is very important. Okay. Very nice. So it's not so easy to explain the cause for each damage, but each damage has its own reason, right?
Yes.
So if you can explain why this kind of damage happened here or there, okay, location, so it means that you understand deeper, right? So it's very important to have interest in such kind of matter. Very nice question.
Okay, thank you, Sensei.
Any other question? Hi. Okay, so I finished today's class, but But the basic philosophy in the first lesson, durability design, and the basic philosophy in the latter second half, seismic design, same. Okay, we need to control the performance of structure. Okay, again, what's performance? Action will come. This structure will behave, right? That's performance, right? So in the case of seismic problem, it's clear. Earthquake will come. The structure will perform. If the seismic performance is not sufficient, it will collapse, okay? Or it will show severe damage. So we want to control performance, right? In the case of durability problem, it's same. Action will come, the structure will perform, but very long term, okay? But it's not so clear compared to seismic design, okay? But it's same, okay? So you already submitted assignment, but after learning seismic design, maybe you will have better image about durability design also. Okay? It's more difficult because it's not so clear, okay? Like seismic design. はい。じゃあ、it's over. So, difficult 2020 is going to be finished. So, see you in January. Okay. Have a nice year. はい。さようなら。See you. はい。バイバイ。
Thank you, Sensei.
Thank you, Sensei.